everybody! In this video we're going to be looking at doing a hypothesis test about a mean. You should have already seen my general hypothesis testing video and also the proportions video. This one's going to kind of build on those. So the process here is going to be very similar to what we saw with the proportions, but we have different test statistics going on. So just like we saw with confidence intervals, when we're talking about means, there's two different formulas we can use. This one on the left would be if we know what the population standard deviation is. And again, this is fairly uncommon. It would be unusual to know this about the population. There are some circumstances where we might know this, but for the most part we're going to be seeing this second case where we don't know the population standard deviation, in which case instead of having a normal distribution we're going to be using that t-distribution again. So this is the same kind of t that we saw with the confidence intervals. So here's our example. Based upon a survey of 58 delay times for flights between New York and LA, the mean delay time was 10.2 minutes. So this is a mean of the sample though, so this is our x bar, with sample standard deviation 31.1 minutes. So this is our standard deviation of the sample. Using significance level 0.05, test the claim that the average delay time is 11 minutes. So the reason we know that we're talking about a mean here is that we're trying to estimate the average delay time of all the flights. So we have the average delay time of the sample, but our question is really, what is that population mean? So our claim that we're testing here, our original claim, is that this mean is 11 minutes. So our mu would be 11. Now remember, we need our opposite claim. In this case, the opposite of mu equals 11 would be mu not equal to 11. And then from these we'll get our null hypothesis. Remember, the null hypothesis always has an equals, so this would be mu equals 11. And our alternative hypothesis, which is the one of these two that does not contain equals, which in this case would be mu not equal to 11. So because our alternative hypothesis here is a not equal to, this is actually a two-tailed test. Right? We don't have a less than or a greater than, so we're dealing actually with both tails here. In the proportion video we saw we had just a right-tailed test, so this is going to be a two-tailed test. And for either of the two methods that we're going to be using, we will need to compute the test statistic. Now this could in general be either a z or a t, but in this case we do not know the standard deviation of the population, so we're going to use that t-test statistic. And this was our x bar, the sample mean, minus mu, which again is sort of the population mean that we're assuming for our null hypothesis, over, and then we have little s over root n. So in this case this is 10.2 minus 11, right? We're assuming that our population mean is 11 for this null hypothesis. 31.1 was our standard deviation, and n again is how many things in the sample were there. Well, in this case we surveyed 58 delay times, so this is a 58 here. So if we plug all this into our formula, we come up with negative 0.1959. Right? This is negative because our sample mean is actually smaller than our population mean in this case, and that's okay. So we're going to take this test statistic and do either the critical value method or the p-value method. So these work very similarly to what we saw with the proportions. We're thinking about kind of drawing our little curve here, but instead of just having one tail, because this is a two-tailed test, I'm imagining having two tails, right, one on the right and one on the left. And for the critical value method, we're going to need to know, well, what are the critical values here? And you will actually have sort of two critical values in this case since it's a two-tailed test, but really we're just going to be looking at the positive one. The negative one would be the mirror image. So the critical value is a t-value where the area in both of these tails, right, so both of these put together are the critical region. And our critical region in this case has area alpha. So in this case we had a 0.05 significance level. So our critical region is going to have area 0.05. You could also think of this as having 0.95 area in the middle, sort of like we talked about with our confidence intervals, like a 95% confidence interval. So we have 0.05 area in both tails. So if we look in the t-score table, we're going to be looking for area in two tails of 0.05, and our degrees of freedom in this case, just like with the confidence intervals, is one less than our sample size, which in this case would be 57. Now, if you look in the table, there isn't actually a 57 degrees of freedom. It doesn't have anything between 50 and 60. So typically we're just going to use whichever is closer. So I'll go ahead and just use 60 as my degrees of freedom here. So the critical value we come up with is a t-value of exactly 2 in this case, 2.000. So that was, again, degrees of freedom 60 and area in both tails of 0.05. So if our critical value is 2, this one over here would be a -2, then we ask, okay, is this test statistic that we computed in the critical region? And in this case, it definitely is not. -0.1 or -0.2 about is pretty close to the center, so it's really nowhere near the tails. Since it's not in the critical region, we would say that this test statistic or our null hypothesis is not unlikely to be true. In fact, it is fairly likely to be true. So we would fail to reject the null hypothesis H0. There is not enough evidence to reject this claim. It seems like the claim could be true. Our parallel method, the p-value method, in this case we're still thinking about the same kind of picture. We've got our distribution here, and we still have two tails. It's still a two-tailed test. But our p-value method, remember, instead of using a critical number, looking up a critical number, we're just going to look up our test statistic. So our test statistic is negative in this case, so that would be this one on the left here. So we're looking at t equals -0.1959 here. And because we have a two-tailed test, our p-value is 2 times the area in this tail, or in other words, we're looking at two tails. So we're going to figure out what this area to the left here is, and then we'll just multiply it by 2 to figure this out. Now, again, this is not a normal distribution. This is not using z-scores, so we can't use the z-score table. What we could do is use the t-table, and again, using degrees of freedom 60, since that was the closest, we could look in the row 60 and try and find which one is closest to 1.959 or -1.959. But all the t-values in the row 60 are bigger than 1. So really, the area that we're looking at in one tail is larger than even the largest value in the table. So the largest area in the table for two tails is 0.2, or essentially 20%. So ours is actually larger than that. Really, if you're going to use the p-value method on a t-value problem, you're better off just using the calculator, because that will give you a better idea of the p-value. We will look at that next. But if our area is larger than 0.2, we would then say, okay, is this a lower probability than alpha? This is not smaller than alpha, which was 0.05 in this case. So again, we fail to reject our null hypothesis H0. The mean problems are a really good opportunity to use the calculator because it can be tricky to find the p-value when we have to use the t-value table. So if we go into our stat button over to tests, we're looking in this case for a t-test. Now you'll see up at the top here we can do a z-test or a t-test. These are both relevant for finding a hypothesis test with a mean, but we're going to use the t-test since we again did not have the population standard deviation. So we're using the stats option. Again, this mu0 is coming from our null hypothesis. So since our h0 was mu equals 11, here we're going to put in mu0 as 11. Then x bar from our information was 10.2, and our sample standard deviation was 31.1. The n value, this was the number of things in the sample, was 58, so we could put in 58 here. And then our alternative hypothesis for this one, this was our two-tailed test, our alternative hypothesis was mu not equal to 11, so that's this first option here. And then we do calculate. So again, we have mu not equal to 11, that's our alternative hypothesis. It gives us that test statistic. This should be at least close to what we computed before. And then here is the p-value. So the actual p-value, again, this represents the probability, essentially, that our that our null hypothesis is true. Our p-value is 0.8454 if I round to 4 decimal places. We can see that this is clearly much larger than 0.2, which is what we found from the table. This is really a very good chance of having the null hypothesis be true. So with a p-value this high, we would say we will fail to reject h0. And then before we finish the problem, we want to again say, well, what does this really mean? If we fail to reject h0, then that means that we're sort of saying, not necessarily that this is true, but it seems like it might be true. So we would say here that there is not enough evidence to reject the claim that the mean delay time is 11 minutes. Or in other words, we think that it probably is 11 minutes, or at least could be 11 minutes. We can't say that it's 11 minutes for certain. It just seems like that could be the case here. There's a good chance. Here's a problem for you to try. Again, this is about a mean of a population. And that's it for this video. Thanks. See you next time.